Alright, so for part 2 notes, we're talking about geometric sequences. Last time we talked about arithmetic, which is where we added something every time. If a sequence is geometric, it means in each successive term we are multiplying by something. So here are two examples. We start with 4, and then it goes to 8, 16, 32, 64. And so you'd be able to recognize this pattern, and you'd see that it, meaning the term, is multiplied by 2 every time. So this is an example of a geometric sequence, and this 2, the thing we multiply by, we call the common ratio. So in arithmetic, it was the common difference, the thing we added. In geometric, when we're multiplying by something every time, it's called the common ratio. Another example over here, 10, 5, 5 halves, 5 fourths, 5 eighths. And so you'll see that it's cut in half every time, meaning we're dividing by 2, but that's the same thing as multiplying by 1/2. So we always describe it as being multiplied by something. So if we multiply by 1/2, multiply by 1/2, multiply by 1/2, etc., so we could say that the common ratio is 1/2. Notice how if the common ratio is less than 1, okay, so like here's 0, number line here's 1, and here's -1. So if the common ratio is within here, the terms get smaller, or closer and closer to 0, and that'll come into play later. If the common ratio is out here or out here, the terms are going to get bigger or diverge, we say. So they'll be either going, well, yeah, I have a graph later. Okay, so recursive formula. Any term is equal to the common ratio times the term before it. Let's write out those words. This notation is sometimes confusing for students. So this is term before, keep it simple, and this is the term. And this R is the common ratio. So we're seeing that we multiply common ratio. We're seeing that we multiply by something every time. So any term is equal to the previous term times the common ratio. Alright, so this is sort of the general way of coming up with a recursive formula for a geometric sequence. Here's an example, 3, 6, 12, 24. So there's a pattern. We're starting with 3, but we double and we double and we double. Therefore, common ratio in this case would be 2. So what do I say? Oh, well, that's all we say. So common ratio is 2. And we could also say that a sub 1, the first term, is 3. And we'll do more with that later. Another example. So let's see. 4 8/3, 16 ninths, 32 27ths. So take a look. This is like a 4 over 1. And what happens to the numerator? Multiply by 2. Multiply by 2, multiply by 2, and what happens to the denominator? Multiply by 3, multiply by 3, and multiply by 3. Therefore, what we're doing, if we're multiplying the numerator by 2 and the denominator by 3, we could say that the common ratio is 2/3. This is what we are multiplying by every time. And you can always find that by doing this divided by this. And if you want to work that out, you'll get this. Or this divided by this, simplify it, you'll get this. This divided by this, simplify, you'll get this. Common ratio. Okay. So that's how to find a recursive formula. And we should write the formula here. Sorry. We need blue. So our recursive formula would be that a sub n is equal to 2a sub n minus 1. For this example, and our recursive formula here would be a sub n equals 2/3 a sub n minus 1. Alright. Next up, explicit formula. So again, recursive formula is where we get a term in relation to the term before it. Explicit is where we get a formula for the term simply as a function of the term number. So, just to refresh our memories, this is our sequence, and this is n equals 1, n equals 2, n equals 3, n equals 4, etc. By n, we mean the term number. This is the first, second, third, fourth term in this sequence. Okay, we could also say that a sub 1, meaning the value of the first term, is 3. We could also say a sub 2, the value of the second term is 6. A sub 4, the value of the fourth term is 24, etc. Okay, so just to refamiliarize ourselves with the notation and whatnot. So an explicit formula, here is in general how we can figure this out. We say that any term is going to be equal to the first term, and then it will have been multiplied by the common ratio, n minus 1 times. So for example, to find 6 from this, right, the value of the second term, we'd have our first term, 3, times our common ratio, which is 2, and then to the 2 minus 1. So let me write that out. That was a bunch of words. So we can say a sub n equals our first term, 3, times our common ratio, which is 2, multiplied by 2, multiplied by 2, multiplied by 2, we already figured that out up above, and then to the n minus 1. So, general formula here, where we can find the value of a term based on the term number. So, what's the 100th term in the sequence? You can just plug in 100, and voila, there's your number. Okay, so same thing, we're trying to find an explicit formula. This is our example from previously. And we could say that the term will be the first term, value of the first term, times the common ratio, and our common ratio is 2/3, to the n minus 1. Alright, so last week we recognized patterns and we tried to come up with formulas by ourselves. Here, so these, what are we looking for? Yeah. So these are basically general formulas that you will probably help if you're trying to come up with an explicit or a recursive formula. So again, these are both for geometric. And in the notes last time, so part 1, so geometric, we looked at the same for arithmetic. So now you have tools, you have 4 formulas. You got this guy, and then 2 from notes last time that will help you figure out either a recursive or explicit formula for arithmetic or geometric sequence. Whew. Okay, so we will be finding sums of these things. Alright, so partial sums, we've talked about this. And just a little note here, a series of numbers is just the numbers listed, and we call it a sequence if we're actually adding them together. Just a little note on technical vocabulary. So, finding the nth partial sum, here's another incredibly useful formula. Right, and so this applies to geometric. Series, meaning a sequence of numbers being added together, where we have the value of the first term and 1 minus common ratio to the n, and then 1 minus common ratio. The derivation of this is kind of cool. You could ask about that, and I can show you, but we're not going to spend the time doing that. So, example, find the sum of the first 5 terms. So we see we got 1, and then 0.7, and 0.49. So we have to figure out the common ratio first, all right? Well, even before that, we figure out, is it geometric or arithmetic? So it looks like I'm recognizing 49 is 7 times 7, so it looks like we're multiplying by 0.7 every time. You can always, so right here, you can always find r, the common ratio, by dividing. So you take, let me get a little more of this in here. You can take this divided by this, see what it is. You can take this divided by this, see what it is. And the numbers over here, you can take this divided by this and see what it is. So when we divide, we're going to get 0.7. When we divide, we're going to get 0.7. So it's the same thing, meaning this is the common ratio. So this is just a little trick that we can always use to figure out, is it geometric? And if we divide every time and get the same thing, then yes, it's geometric. Okay, so finding the sum of the first 5 terms. So we first determine that a sub 1, the value of the first term is 1, and then the thing we multiply by, the common ratio, is 0.7. So we have 1 as the value of our first term. We have our common ratio is 0.7, and so we're substituting it in here. Notice how I called this S sub 5, meaning the sum of the first 5 terms. N is 5, that is the number of terms, and we get 2.7731. So if this is just weird and you're like, I have no idea what this means, you get this, you're like, I have no idea if that's correct, you can always add them up, right? And if it's just the first 5 terms, that won't take a whole long time. 1 plus 0.7 plus 0.49 plus blah 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 plus blah blah blah, and it's the exact same. Whoa, how'd I get these numbers? I took this multiplied by 0.7. I took this multiplied by 0.7. Yes. Okay. So that's cool, but there's something even cooler, and that is you can add up an infinite number of numbers and end up with some finite number. So this is where math actually starts getting exciting. Not that it wasn't exciting before, but in my opinion, this is a big step. Let's put it that way. Okay. So we have a sequence of numbers added together. We call that a series. It's infinite if we're adding up an infinite number of them. So we're adding up all numbers in a sequence forever and ever. So that's kind of weird, but check out what happens. So we call a series convergent if the values, so as the term number increases and increases and increases, they're getting closer and closer and closer to 0. And just thinking geometrically, okay, so let's say we have some number here, and we have another number, and another number, and another number, and another number, another number, another number, and I could sit here all day and do this, this, and this is actually going to do this. We could, if this were paper, we could cut this out. This has some specific area, and when we add them all up, it would be that area. So even though there's an infinite number of numbers, they get infinitesimally small, so we can add them up and get some actual number, a finite value. It's divergent, we say, if the numbers get bigger and bigger, so this increases and increases and increases and increases, and it keeps going like that. So there's never some actual finite area that you could cut out of a sheet of paper and find the value of. So difference between divergent and convergent is they get smaller, okay, or closer to 0. Let's write that. I think it's somewhere on here, but I'm going to write it again. Closer to 0, and divergent if they get farther from 0. They get bigger. Okay. So take a look at our formula. I know it got a little messy here, but this is the formula for the sum of some series of numbers. And if it's infinite, see how I've plugged in n equals infinity? So if we look at this, what happens, remember our common ratio is going to be something less than 1. So if you did 1/2 to the infinity, or even, you're sitting in front of a calculator, try that. It's going to be a really small number. Bigger the exponent gets, the closer and closer this gets to 0. So when we talk about r as something that's less than 1 to the infinity, this is basically 0. So if this is 0, we have a sub 1 times 1 over 1 minus r. And our formula simplifies to this. That's a sub 1, the value of the first term. So this is sum of infinite geometric series. Add up an infinite number of numbers that get infinitesimally small. And you actually end up with a value. So you should ask, I need to tell you the Snickers bar story. One person asked last week, but ask. It's related to this. Okay, so, and then over here, this is more specifics. So if r is greater than 1, and we say absolute value because you could have 2 or negative 2, the series diverges and there is no sum. But if the absolute value of r is less than 1, it converges and we can find the sum. So here's our question. Example, determine if the series diverges or converges. If it converges, find the sum. So we look at it first and we're like, arithmetic or geometric, and it looks like we're multiplying by something every time. So once we have found what we multiply by, we know it is geometric. Looks like our common ratio is 1/5. And again, if finding this is confusing, you can always do this divided by this, and you'll get this. And then you do this divided by this, and you'll get this. And you do this divided by this, and you'll get this. And you say, aha, it's 1/5 every time. So that's my common ratio. Value of the first term is 2. So because this 1/5 is closer to 0 than 1 or negative 1, another way of saying that is the absolute value of 1/5 is less than 1. The series converges, values get closer to 0, and we can just substitute in. So I labeled this as the infinite sum, little infinity there. Value of the first term, 1 minus r, and we get 5/2. So it'd be fun, if you're bored at home, you could add these up in the calculator, and you'd have 2 over 625, and then 2 over, and these big numbers, and it'd get closer and closer and closer to 2.5 as you went on. Thanks for listening.